Okay, so
Today we're learning Riemann sums.
so disappointing.
Alright, take 26.
Some people call these Riemann sums. I've always called them Riemann sums. But a Riemann sum is a way of approximating area. First semester we did derivatives, and if you had to sum up derivatives in one word, what would that word be?
Challenging.
Slopes. Right? Integrals, if you have to sum up what an integral is in one word, does anyone know what it would be?
Area.
Area. An integral finds area under a curve or in between multiple curves. So to start the lesson on, or the unit on integrals, we're going to start by learning how to approximate area. Just like with derivatives, we had to learn the long way for derivatives first, with the limit as h approaches 0 of fx plus h minus fx over h. With integrals, we have to learn the long way first so you understand the basis of what an integral is. And the mathematician Riemann came up with a way of approximating area under a curve. There are lots and lots of ways to approximate area under a curve. Today, all of the ways we use will all focus on rectangles. So we're going to use rectangles to approximate area. There are so many different types of rectangles that I'm going to give you just a quick visual on what they each look like, just so you understand. So say we wanted to find the area of this region, and it's always, for our purposes, the area between the curve and the x-axis. Alright, so we're always talking about the area between the curve and the x-axis from some starting point and some ending point, a lower bound and an upper bound, right? So we have our lower bound and our upper bound. So we split the region into a certain number of intervals, and the problems will tell you how many. It's usually 4, but sometimes it's not. And the first type of rectangles we're going to learn are called upper, or in some texts you'll see them called circumscribed rectangles. And if you look at each interval has two sides, and both sides stop when they hit the function, right? So you have your two sides of your rectangle. Obviously this isn't a rectangle yet, but you have your two sides. Each side stops wherever it hits the function. The one that stops at a higher point, that determines the height of your rectangle. So these rectangles, that first one would be like that. And then the second rectangle between here and here would be like that. And the third rectangle between here and here would be like that. And the fourth rectangle would connect up here and look like that. Now the problem with upper sums is that they are always what compared to the actual area?
Greater.
They're always greater than the actual area. That's why they're called an upper sum, right? Because they're always, if you added the areas of these 4 rectangles together, that total would obviously be bigger than the actual area under that curve. Okay, so that's called an upper sum. Where there's an upper sum, there's a lower sum. Anyone know the opposite of circumscribed?
Uncircumscribed.
Oh.
Not.
Inscribed. Lower or inscribed rectangles. So for lower or inscribed rectangles, you take the two heights on each side of the rectangle, and the lower one determines the height of your rectangle.
And you go to the last.
Like that. Alright, so each one, you have these y values where the sides hit the graph. The lower one gives you the height of your rectangle. Okay. The College Board does not use upper or lower rectangles very often. More often, they use these types. the first type that they use is called a left rectangle, or a left, some people call them left-handed. I tend to call them left-handed. A left-handed rectangle. Now if you look at each rectangle, it has a left side and a right side. The left side determines the height of the rectangle. So it doesn't matter if it's higher or lower, whichever side is on the left, that's the height you use for your rectangle. So left, left, left. Left-handed rectangles are always higher than the actual value when the function is decreasing, and lower than the actual value when the function is increasing. Okay, where there's left-handed,
There's right-handed.
yes.
Sure. Right-handed extrusion.
My function's slightly changing shape. That's okay. All right, so a right-handed, same thing, except it's the right-handed side that determines the height of your rectangles. So left and right, use the right one to determine the height. And that's kind of low. Yeah, absolutely. All right, there's one more type of rectangle. Then there's another shape we're going to learn tomorrow. We've done above, we've done below, we've done left, we've done right.
In between.
Yes, that's exactly right. The last type of rectangle that we're going to talk about is a midpoint or middle rectangle. Now midpoint rectangles, it's not the average of the heights, it's whatever the height is at the midpoint in the x values. So you find like this middle point, wherever it hits the function, that's the height of your rectangle.
Is that one the most accurate?
Of these types, that would be the most
How would you
accurate.
know where to start that from? Like, how would you know where to draw the?
They have to tell you. They'll say like from x equals -2 to 2 using 4 midpoint rectangles, and then you would go from -2 to 2 and you would split into your rectangles and then find the midpoints. I'm going to walk you through one. All right, everyone understand the pictures? Because I'm about to erase them.
We can get this other person.
Yes, and actually I need to move the camera so everyone's got this because I didn't move it. Okay, so there on film, there's the right-handed and there's the midpoint. Now, these problems can be, depending on how they are taught, people can think they're complicated and confusing, but they're actually really, really easy. You just have to know how to approach them. I used to teach them in a more complicated way than I do now. Can I erase these two, or are you?
All right, Sam, come on.
Okay.
But you're really the slow one at our table, so are you really complaining? Normally, we have to wait on you all the time.
Y'all can have them back if you want tomorrow.
Yeah. We don't want them back. We like Kayla a lot better than
No,
you.
you don't. You're just saying that.
You're probably the least favorite person we've ever had at this table.
Our first example,
They don't have many people out
We'll
here.
have 5.
we're going to use 6
No, we've had Hannah
rectangles.
Davis too, remember? Let's get 6, or yeah, 6. I saw Hannah Davis at Walmart the other day. She was with her mom. I said hi to her twice, and
Oh,
she was
we
really
used,
reluctant. You saw a monkey?
The guy just walked in, he had a monkey on his shoulder.
That's so cool.
They allow monkeys in Walmart?
Did you see Lori Davis?
I mean, have you seen the people in Walmart? They kind of look like monkeys.
Oh my god.
I mean, no, seriously. Ah, I think I have an ear infection.
Oh, wait, sorry. My wife.
Wait, Miss Price, I have a question.
Yes.
If you're not on Math Street, what street are you on? Did you get put on like English Street or like History Street?
Yeah, are you serious?
Yeah.
I'm on English Street.
You're on English Street?
I am.
Wow, that was my first
Like
guess.
on-level English or like
Mhm.
AP?
Oh, do they have different? Like, do they? Oh, that'd be so cool if
Yeah,
you
what
had
if
like
they
an
talk
AP
to you?
English Street.
They don't know, no one knows what you're talking about, we'll talk about that later. We don't need to put that
I
in
know
here
what
right
she's
now.
talking about.
Okay, so here we go. So we're going to use 6 rectangles to approximate the area of this region using upper, lower, left, and right-handed sums. You do not have to draw a picture to get these problems correct, but I'm going to draw one just so you can see visually what's going on. Alright, so y equals x squared plus 1, that's the curve that's kind of driving this problem. We are going from -1 to 2, that's like our left endpoint, and this is our right endpoint, kind of our starting and our stopping. So we're going from here to here. And we're talking about the area bounded between those two x values, the curve, and the x-axis. So that's the region we're approximating.
6 rectangles.
Okay? Now, when you do these problems, the first thing you want to do, I'm going to walk you through some steps. Step 1 is find the width of your rectangles. Because area of a rectangle is width times height. So first thing we got to do is find the width. In some problems, the widths are changing. They're non-uniform, but in all of your problems tonight, they're all going to be uniform. So we're just going to stick with those for now, and then when we get into more AP type problems, we'll do some with unequal widths. So we're going to find the width. There is a formula for width, and you're going to have to know it, especially for tomorrow. It's b minus a over n. A is your left bound or your left endpoint. B is your right bound or your right endpoint. And n is the number of rectangles you're splitting your region into. So for our problem, B is the right endpoint. You do right minus left over n. So what's the right endpoint?
2.
2. Or think the left bound, right bound. What's the left bound or the left endpoint?
-1.
-1.
That's plus
And then how many rectangles are we using?
6.
6. So we have over 6. So we get 3 over 6. The width of each rectangle is a half. Makes sense, right? The width of the whole region is 3. We're using 6 rectangles, so each one's a half wide. Okay. All right. The next step that you want to do is make a table. When you make your table, this is just going to be like an XY chart. You want to start at your left bound for your x values and then walk by widths. So if we start at -1 and then we go a half over, so now we're at -1/2, then we're at 0, 1/2, 1, 3/2, 2, and when you hit your right bound, you stop. So you start at the left bound and then you just add widths until you get to the right bound and then you stop. Now we gotta find the y values for all of those numbers. So we're plugging each x value into our function. So when x is -1, we get 1 plus 1 is 2. At -1/2, we get that squared is 1/4 plus 1 is 5/4. 0 squared plus 1 is 1. 1/2 squared plus 1 is 5/4. 1 squared plus 1 is 2. 3/2 squared is 9/4 plus 1 is 13/4. And then 2 squared plus 1 is 5. So you plug all your x values into your function, you get your y values. Now, once you've done that, finding the answers is easy. So we have upper, lower, left, and right. For each rectangle, the area is width times height. Since the width is the same for all of them, you can put the width out front and just multiply it by all of the heights added together. So that would be the same as 1/2 times each height. Okay? So for whatever you're doing, you put the width out front and then just put all the heights in here. Okay, these are really easy. You look at each pair of y values. For an upper sum, you look at the first two y values and you pick whichever one is bigger. So between 2 and 5/4, which number is bigger? 2. That's the one you use. Then you go to the next pair. Between 5/4 and 1, which one is bigger? 5/4. So use that one. Then you go to the next pair. For 1 and 5/4, which one's bigger?
5/4.
5/4. Between 5/4 and 2?
2.
2. Between 2 and 13/4?
13/4.
13/4. And then between 13/4 and 5?
5.
5. 6 rectangles, you should have 1, 2, 3, 4, 5, 6 heights. Right? 6 heights, 6 rectangles. And then you're going to use a calculator to figure out the answer, which we'll do in a minute. Lower. So everyone take a second. You're going to do each pair and just pick the lower number. Everyone see if you can find the 6 heights for your lower rectangles.
Sorry, no.
Alright, so what's the first height?
5/4.
What's the next height?
1.
What's the next height?
1.
Good. What's the next height?
5/4.
Then what?
5/4.
2,
Come on, embarrassing.
and then 13/4.
This just off.
Okay? Alright. For a left-handed, left and right are the easiest of all. For left-handed rectangles, you just look at each pair and take the one on the left. So when you have 6 rectangles to do, you do the 6 leftmost heights. So I just look at this pair, which one's on the left? 2. Then 5/4. Then 1. Then 5/4. Then 2. Then 13/4. Be careful, you don't list every single number because this last pair, it's just 13/4 that's on the left. So you use the 6 leftmost heights. And then for right-handed, you do the 6 right-handed heights. What would be our first height for right-handed? 5/4, and you just write every number from there.
Those are my favorites.
Yeah, they're really nice.
I feel like the midpoint one's pretty.
The midpoints we gotta do right now, but it'll just take a minute. Okay, I'll give you numbers for these in just a second. Okay, are there any questions on how to find upper or lower or left or right? Good. Alright, so again, make the table first, and then you just look at each pair and pick whichever it asks for. Upper, lower, left, or right. Midpoint. We're going to kind of do an extension example. So I'm going to do like example part B. So we're going to do ditto using 3 midpoint rectangles. In your book, it's going to give you, the midpoint problems are kind of separate, and it gives you this funky looking formula. Don't let the formula freak you out. The formula is just fancy talk for finding the midpoint and finding the y values at the midpoints. So don't worry about the formula. Here's what we're going to do. First thing we have to do, of course, is find our width. We have a new number of rectangles, so we have a new width. It's still b minus a over n. So it's still 2 minus -1, but now our n is 3. So what is the width of each rectangle for this problem? It's 1. When you make your table for midpoint, here's what I want you to do. You start at your, -1. Start at your left endpoint, and then walk by widths every other little unit here. So -1, 0, 1, 2. So whatever your width is, you're going to walk by those, but do it every other box, because in between you have to put in the midpoints. So the midpoint between -1 and 0 is -3/2. The midpoint between 0 and 1 is 1/2. The midpoint between 1 and 2 is 3/2. Here's what happens. The rectangle from -1 to 0, we want the y value at the midpoint.
Why would you make it a 3/2?
Oh, I'm so sorry. -1/2. We want the y value, thank you. We want the y value at the midpoint. So the y value at the midpoint, -1/2, is 5/4. Then from the rectangle 0 to 1, we want the y value at the midpoint, which is 5/4. And then for the rectangle 1 to 2, we want the y value at the midpoint, which is 13/4. Those are your 3 heights. So for your midpoint approximation, it's the midpoint width, which is 1, times each of your 3 heights, 5/4 plus 5/4 plus 13/4. Now if we compare the numbers, the bell's going to ring in a minute. I'm going to see if I can do these real quick. So 5/4 plus 1 plus 1 plus 13/4. Okay, so this one we get 4.875. By the way, if the upper is 7.3 and the lower is 4.8, what would be a good approximation?
Like,
Average these, right? Which is what we're going to do tomorrow when we do trapezoids. Okay, let's see.
you were really happy when you said trap.
I know. Okay, this one, 5.375. This one is 6.875, and our midpoint $5.75. Quiet please. Of left, right, upper, lower, and midpoint, which one is usually the most accurate?
Midpoint.
The midpoint.
Wait, what? Average them all together. What is it? What is it?
If I average the upper and lower together?
If you average the upper, lower, right, left, and right too.
That doesn't usually work for left and right because part is increasing part, but more
Then
is...
just upper and lower. What is it?
If you do upper and lower together, you get 6.125, which would be your trapezoidal sum. Trapezoids and midpoints are the 2 best approximations. So if you had, this is 5.75 and trapezoids give you 6.125, then around 6 would be
What
your
if you
best
do
approximation.
average of left and right? Is that nothing?
It's something. It's actually pretty close. That would also give you about
Is there a
6.
special name for it, like
No.
ambidextrous something?